Alright, welcome to my video presentation for my internship through microbiology department at Utah Valley University. This has been a project that I started with last year, and then it turned into an internship, and now it's going to be turning into hopefully a published paper, which is going to be awesome. This is through the microbiology department. Even though I'm an aerospace and mechanical engineer, I like to try to bring in multiple different groups to try to do certain things. I believe that science is all about connecting the dots, and that's what this entire presentation is about. Now, I'm going to be doing multiple videos and posting them on YouTube because this is a long subject that could go on for about 2 or 3 hours, but I'm not going to do it all in one sitting, so bear with me. There's going to be a lot of real science and real math, and hopefully this clears up a lot of misnomers in the 3D printing community as well as the regular scientific community because of how all of this started, which I'll get into in just a moment. So a little bit about me. I'm an aerospace and mechanical engineer who has experience within the field of materials and medical devices. I have a minor in drafting. When I say a minor in drafting, actually I have an associate's degree in drafting, and then I have a minor in math. I have 13 semesters of math done. I have a minor in materials because I've done multiple material courses, including advanced materials, and I have courses in medicine such as anatomy, pathophysiology, physiology, chemistry, organic chemistry. I'm a certified phlebotomist, and I have courses in biology and microbiology. Now, if you're curious about some of my projects, you can go ahead and look at these two websites. The first one, the portfolio, lists all of my projects I've done for school, including my favorite one, which is working with a company out in the UK called EDU, I think it's Granta, and they did something called the EDU Pack, which we helped with proving that the material used for the Mars lander that NASA picked was indeed the correct material, and their software helped tremendously with that. I suggest you go and look at the portfolio and look at the presentation or the PDF of it. Then the next one is a group that I spearheaded during COVID for mask relief for the general public as well as first responders when it came to the mask shortage. And that's kind of what spearheaded this entire project I am doing now with Is It Food Safe, is because of COVID and some of the things that were going on with it. And so that moves us into our next slide of my reasons. And with COVID, it's because people are at home now during quarantine. They're going to just start 3D printing stuff. And I got a lot of questions about, are cookie cutters food safe? What about spoons and forks and bowls and all these things I 3D print? What if I print a toy and my baby's chewing on it, and then can we wash it and then give it back, and so forth? A lot of great questions. And when we spearheaded the mask group, we printed 2.2 million devices. We had 350 people, and we printed 2.2 million devices. That includes face shields, masks, ear savers, and the valves that they used in certain breathing machines. I forget what they're called. Some people did nose swabs with resin printers. I didn't get into that. I only stuck with face shields, masks, and ear savers. But the reason why that helped spearhead this entire thing is because all of a sudden we got this question of, well, can these masks and face shields and ear savers be washed? I mean, they got rubbing alcohol, but that started to be in short supply too. Bleach water was starting to be in short supply, so what was left was basic soap and water. And the answer to that question is absolutely they can be cleaned with soapy water and sterilized. Not sanitized, but sterilized. I might have that backwards. I'm going to have to look it up. One of them means it removes sanitization when it removes enough bacteria and pathogens to a safe level. Sterilize means it gets rid of everything. It's completely sterile. It's like nothing is on there except the dead skeletons of your enemies of bacteria and pathogens. It's just nothing there. It's a barren wasteland. So, to answer the question, can 3D printed parts be sanitized? The answer is yes. And I'll get into that. That's the whole point of this presentation. Okay, Another reason I got into it is there's so much fake science out there that, okay, yeah, I can help shed light on truth and how real science works. Because I don't know what happened to the world in 2020. Because in 2019, some of my friends, a lot of my friends, even in 2018, 2017, 2015, I was talking to about viruses and bacteria. They knew how it worked. They knew how masks worked. I talked to them all the time. And they don't have degrees in science, but they had a fifth grade biology book, and they read about viruses, and we were talking about it, and it wasn't just normal random conversation of, oh, do you know how bacteria... We had a point of why we were talking. It wasn't just because we were bored. But like in 2017, I went to an Instacare because one of my friends broke his arm from snowboarding. And in the Instacare, they had about 12 people who had the flu. And so they told us to wear a mask because they have a small little outbreak of flu in that city and in that particular Instacare. And we're like, yeah, no problem, no problem. And we were fine. 2020 rolled around, all hell breaks loose. All of a sudden, my friends who were understanding fifth grade biology all of a sudden were following these weird trends with science and began posting things on the University of YouTube and became self-proclaimed doctors of science and medicine and all this stuff. It was crazy. And which leads to too much inaccurate info, because when you have fake science, it's enough to be dangerous. They give just enough information, just enough real science to sound good and pleasing and promising, and then they stop. And then it becomes dangerous because they leave it up to you to come up with a conclusion. That's like me saying, well, is it food safe? And saying, you know what, we've done all these tests and we have found that it's this and this and this, and then never stating the answer at the end and leaving you to your own devices to say, oh yeah, he means it is food safe. Oh yeah, that video totally means it's food safe. And then some people are like, no, it doesn't mean food safe at all, and then this whole conglomeration of mass confusion. And that's why I started this entire project last year, is to shed some light on a world that all of a sudden went chaotic for no apparent reason. So, with that in mind, let's talk about a few simple things. Viruses and bacteria. Okay? We'll talk about the images on the left here in a minute. So this is how viruses and bacteria work. First, let's start off with a virus. According to the Encyclopedia of Medicine, a virus is just a sub-microscopic infectious agent of very simple composition that replicates only, keyword, only inside much larger living organisms. It's that simple. They only replicate inside much larger living organisms. Because viruses are non-living, they cannot replicate by themselves. They require a living host. And fun fact, the specific size that allows successful replication of a virus is 0.4 microns. It has to be that large, or the virus cannot successfully replicate. That study was actually done in the early 60s, I think it was 1962, where they found the smallest possible size for an influenza virus to actually successfully replicate. Then they did it with other viruses, and it turns out other viruses are the same. All coronavirus type, which is 256 types of viruses. Corona just means a crown, because it has a crown that looks like thorns. So the cold is a coronavirus, the flu is a coronavirus. They're all respiratory viruses. Anyways, they're just, they can't replicate by themselves. They require a much larger host that's at least 0.4 microns, because they need its organelles, they need its food supply, its energy, all of its resources to allow the replication, because it does its replication for it. It's kind of like children, anyway, when a woman's pregnant, I mean, you could think of as a baby as a parasite. It's living off the host. That's an interesting analogy. Anyway, okay, bacteria. Now, bacteria are living organisms much larger than viruses. Viruses are 0.125 in microns, but remember, they don't just sit out in nowhere. They have to be in a living cell. And fun fact, we do not breathe out viruses. I repeat that. We do not breathe out viruses. We do not breathe out a naked virus. We breathe out infected host cells. And those host cells are large, 0.4 microns and larger. Even if you sneeze and you break up those host cells into smaller nuclei, they're still pretty large. And as you break it apart, those smaller ones, they say that the sneeze, you can get particles probably closer to the size of viruses than bacteria. So we're talking, like 0.1, maybe 0.2 microns from a sneeze. But then at that stage, that infected cell is too small to really do anything because it doesn't allow for replication. However, later on when I talk about filtration tests, you'll see that those actually are easily blocked because people misunderstand how masks work completely. Anyways, so bacteria have 3 different types of categories. There is psychrophilic, mesophilic, and thermophilic. First one is they like to live in cold. The second one is they like a middle temperature. And the third one is they like heat. There's some viruses that live at 175 degrees Fahrenheit. So, luckily the foodborne illnesses don't live there. Foodborne illnesses only exist in the middle range. And their perfect prime temperature for them is 98.6 degrees. Isn't that interesting? So, okay, the first ones are the ones that live in cold. Like, we're talking, those are the ones responsible for the food that spoil in your fridge. Those are those guys. They like the cold. Anyways, okay, so this leads to something called surface tension. Because, and people are thinking, so why does surface tension? I mean, you just totally went from viruses, bacteria to a totally different subject. Actually, they're extremely related. Because surface tension is the property of a liquid that allows it to flow, to resist external force. So if you have a drop of water sitting on a piece of plastic, you'll notice it beads up and you kind of get a spherical shape. That's because it's not allowed to flow. The hydrogen bonds are like tight rubber bands, and it's not allowed to flow. But if you put rubbing alcohol on the same piece of plastic, you'll notice it flows more. That's because the hydrogen bonds are looser. And so it doesn't resist the external force of gravity or whatever, the pressure gradient of whatever elevation you're at. It doesn't resist it that well, so it is allowed to flow. It also has something called the wetting angle, which is above a certain degree measure, you're going to have very poor flow, but below a certain measure, you're going to have very excellent flow. Turns out that soapy water actually has a really low surface tension. I mean, soap is amazing. It kills things by turning other cells into soap because sodium hydroxide, or lye, takes fat and oils and turns it into soap. It saponifies it, or saponification, or soap for short, and turns it into soap. And it's very caustic. It's toxic to bacteria because it literally rips them apart and turns them into soap. And if viruses live inside of bacteria, it's called a bacteriophage. It lives inside of bacteria or another living host cell, and host cells are made of lipids, which is oil. They get ripped apart, and then those viruses just get flushed away. So that's why washing your hands is important. Turns out that soapy water has a surface tension of 24 dynes per centimeter. That's a force over area. And it can get into pores as small as viruses, which I think is really cool. Remember, viruses are 0.125 by themselves, dead on a microscope tray. Like, you see a dead virus, it's not technically dead, dormant virus. It's not in a host cell. They are 0.125 microns. But remember, they replicate inside of host cells, and that's what we care about. And host cells are very large, 0.4 microns and above. And foodborne illnesses require a certain length. Some of them are 10 microns. so they at least require 10 microns of space to house themselves. And then, at least on the surface, they can spread out, but in pores and dimples, they need a lot of space. Okay, so now this leads to rubbing alcohol, which is actually a very low surface tension. It's about 22 dynes, so it can get into pores smaller than viruses. It's actually required by law to use rubbing alcohol of 70% or higher in medical facilities, manufacturing facilities, and at the lab I'm at, we don't use anything else but 70% rubbing alcohol. It's just, it does its job, and that's what we use. We don't even use bleach water. We just use straight up 70% rubbing alcohol. It works great. So, remember that soapy water, rubbing alcohol can flow into pores as small as viruses. That is an important key concept when it comes to 3D printing. Alright, so this is where I'm currently going to stop, and this is where we will begin for the next slide. But don't get scared. Don't get scared of all this math. I will explain it. So this is where I'm going to stop for tonight, and then we will continue again and move forward. So thank you for watching, and I hope you enjoy.